In this video, I'll show you how to find the voltage gain of the resonance tank of the LLC converter. So this is the resonance tank. Now if you simplify it, you will get this circuit. So you simply just replace this half bridge with a voltage source and this whole thing here with a resistance. This would actually be a square wave, but we're only looking at the first harmonic, so we assume that it is sinusoidal. Now we set the voltage gain of the resonance tank equal to G. So this is VO over VE. So it's the equivalent values. So we want to express this voltage gain as a function of the parameters in the resonance tank. So the output voltage could be written as the current multiplied by the resistance going to the output. So it will become I equivalent and then multiplied by Lm in parallel with R equivalent. So you simply multiply this impedance with the current flowing through it. And we can use a similar method to find the input voltage. So we have that VI equivalent equals IE. So the input voltage would be equal to the current flowing through all of this resistance. So we just have to add all of these and multiply it with the current. So we have II equivalent and then multiplied by SLR plus 1 over SCR, because those are the impedances of this series here. And then plus the parallel. So these should be the voltages. So if we just divide this one with this one, we get the gain. So the current goes with the current. So then we just have the parallel over SLR plus 1 over SCR, and then plus the parallel. So this is the voltage gain that we get. If one simplify the gain, one get this equation. So omega is the per unit value of the switching frequency with a base of omega r, which is the resonance frequency. And it is given by this equation. And then we have M, which says something about the ratio between Lm and Lr. I will come back to that later. And then we have Q, which is the quality factor, and it depends on Re, which is the output resistance. So if we have high load, we have a low Re, which results in a high quality factor. So this plot is plotted for different quality factors. So with a high load, we get this waveform. And then with a low load, we get the blue one. And this plot is plotted with Python. So this is the code. It is also in the bio if you want to use that. And if you use MATLAB, you can just convert this into MATLAB by using ChatGPT. So on the y-axis, we have the gain. And on the x-axis, we have the switching frequency in per unit value. So at 1, the switching frequency is equal to the resonance frequency, as you see with this equation. So you can see that the gain is always equal to 1 when the switching frequency is equal to the resonance frequency. And you can also get that from this equation. If you just set this to 1, you will get 1 of this equation. Now you can see that there are kind of like two peaks in this gain. So we have one here and then one here. So this is due to the resonance between LR and CR. And this peak here is due to the resonance between LR plus LM with CR. So that is what M says. It's kind of like the ratio between the resonances. And the resonance frequency is given by this. So if one increase LM, the frequency will be lower because the inductance will be lower. Increasing M will move the second resonance to the left, and decreasing M will move it to the right. The reason why we get two different resonance frequencies is because of this parallel here. So when Re is very low, this Lm can basically be neglected because all of the current will flow through Re. However, if Re is very high, no current will go through Re. Everything will go through Lm. and therefore we have different resonances. Because if it goes through here, then we have larger impedance, larger inductance, I mean. And if it goes through here, then we have a lower inductance. So usually one design the LLC such that, for example, the yellow one is the worst case, the case where you have the highest load. So if you then increase the switching frequency, you will get a lower gain. And if you decrease the switching frequency, you will get a higher gain. However, if you have too much load, you will get a lower gain when you also decrease the switching frequency. So it's important to design it well. So it's important that you design it well such that the worst case, it also increases.